Okay, so let's look at the end behavior of a rational function. The end behavior occurs when the domain variable x goes towards positive infinity and negative infinity. We saw this with polynomial functions. We know that Rx equals 1 over x has a horizontal asymptote at y equals 0, and the same for R of x equals 1x curved, because as x gets infinitely big, or small, meaning positive infinity or negative infinity. So as x gets closer to infinity or x gets to negative infinity, 1 over x is approaching 0. Okay, and 1 over x squared is also approaching 0. So both of these are approaching 0 as x gets really big or x gets really small, going to the infinities. Okay, all right. So now let's look at a more complicated rational function. Given a rational function, r of x equals n of x dx, if the degree of the numerator is, let's say, less than. So it's less than degree of dx, then the horizontal asymptote is y equals 0. Same thing. So in a case where, again, the numerator degree is less than the denominator degree, the horizontal asymptote is at 0. Given the rational function r of x and x over dx, if the degree of n is the same as degree of dx, then the horizontal asymptote is what? The ratio of leading coefficients. Of numerator and denominator. Okay. Given the rational function r of x equals nx dx, if the degree of nx is greater than dx by 1 degree, then there is no horizontal asymptote. Instead, there is an oblique, what's called oblique, or slant asymptote. So it's neither vertical nor horizontal. It's at a slant. Okay. So we're not going to deal with this. We're just going to look at these two cases here. Okay. There's even a third case. What happens is if it's greater by 1 degree, if it's greater by more, then it starts looking like, well, you'll see in a second. So to make sense of this, we think about, again, the end behavior of rational function. Let's look at an example. I have this, again, you see it's a polynomial divided by a polynomial. Fantastic. But the end behavior is determined by the largest degree, the degree of the polynomial. So it has to be the largest term, the term with the highest power. So remember, the first term, if I were to multiply it together, I'm not going to. That'll take a while. So I'm going to figure out where the variables are. So the term, the highest term will come from the first times the first times the first. So in other words, multiply all these with the variables in it, and I get 2 to the x times negative x times 3 to the x, and what do I get? That gives me x cubed, and the number here is 2 times -1 is -2 times -6. So I got -6x cubed. That is the numerator. The denominator now becomes 4x times x times x. So that gives me 4x cubed. So the leading terms of R of x is this -6x cubed over 4x cubed. Now, how does that help me? Okay, so here's what's going on. For a polynomial, remember we said the polynomial size has nothing to do with how many terms it has. It has everything to do with the highest power. And why is that? Because if you start looking at the output of each term, if I were to multiply this out, eventually, since we're going, the end behavior is when we go to infinity, the one with the highest power starts producing numbers so large that it eclipses anything that came before. So the other powers, or the other terms with different powers that are lower, they stop producing as much, and these two will eclipse the other ones. So what we're saying is as x approaches positive or negative infinity, R of x, this whole thing, is getting closer to what? -6x cubed over 4x cubed. Okay, that's what it's approaching. And now if I clean this up, I can, cancel the x cubed, and then I see I have power. I have a common factor of -2, or 2, I should say, for both. So divide by 2, divide by 2. So this gives me the horizontal asymptote. So the horizontal asymptote occurs at y equals -3 halves. So this tells us again, when we go towards infinity, all of a sudden the rest of the terms don't really matter. The only thing that's controlling the output mostly is these two terms. So I can cancel again. If I have x cubed, I'm starting to numbers over x cubed that can produce the same number, so I can cancel them out, and this is the only thing that's left behind. Okay, what is the end behavior of the rational function? Blah blah blah. So again, same thing. I'm going to have to factor this. So let me factor first. So I've got 5 as a prime. 5. Oh, actually, that's sorry. I'd rather factor. Sorry, I'm looking at the end behavior. What was I thinking? So again, I noticed that. So what we have is this: as x gets really big, this term and this term are not producing much as that. So as x approaches infinity or negative infinity, so let's go pause. Then what's happening to this function? R of x is approximately equal to these highest terms. So rx to the 5th, 6x to the 7th. So now we will notice that the degree of the denominator is bigger than the degree of the numerator. So all of a sudden, as these start climbing up, this one will climb higher, faster than this one. So as that happens, the ratio would be approximately equal to this, but then this is just approaching 0. Okay, because this one's climbing faster than this one. So the horizontal asymptote is at y equals 0. Again, the degree of the denominator is bigger than the degree of the numerator. What is the end behavior of the following function? Okay. So again, I'm going to have to multiply this out. So to get that leading coefficient, I'm gonna just pretend that I'm not gonna multiply the whole thing out, but what I have here is this 3x times x, and this is x squared. So what I have here is the numerator. So as x approaches positive or negative infinity, r of x is approximating, and then I have the numerator 3x times x squared. The denominator is 10x times x. Yep, that's it. So what I have here now is 3x cubed, 10x squared. If I were to again reduce this, I could have reduced that one, but I didn't. Get the point. What happens is when I reduce this, what I have is 3/10 and then x. So this is an oblique asymptote. So what does that mean? If I were to graph this, right, I'm not going to graph this function. I'm just going to graph what this means is that at 3/10 x, so again, that's your slope. So imagine, okay, this is 10, 10. So this is an approximation. So it's a run of 10 up 3, run of 10 up 3, so it's about right here. Yeah, I'm not trying to be precise here. Run of 10 down 3, somewhere here. Imagine I'm going to draw a line, straight line through this. So as x gets really, really big, or x gets really, really small, all of a sudden this graph looks like something, but eventually you're going to see that this thing is going to start either curving like this or maybe coming underneath. I just don't know what this thing looks like just yet, but all of a sudden, maybe I'm just going to guess that maybe it looks something like this, but at the infinities. All of a sudden, the larger this gets or the smaller this gets, the graph just starts getting closer and closer to this line right here. So it's not a horizontal asymptote. It's not a vertical asymptote. It's an oblique one. So it means it's literally a line. And why? Because the degree of this is just one higher than the degree of that one. But we're not going to graph these oblique ones.